Okay. So till now we have discussed with our topic, that is gravitation. So first we'll recall what we all have studied. Okay. So first we started with the definition of gravitation. What was gravitation? It was a non-contact force of attraction. It was a non-contact force of attraction between any two bodies in the universe, and no matter how far they were, right? No matter how far the bodies are. Similarly, the two bodies can be the earth and the any body which is kept on the surface of the earth. So because of which we have written the statement that the earth attracts or pulls all the bodies center towards its center. The force with which the earth pulls the bodies towards it, it's called as the gravitational force of earth or gravity of earth. So because of which we write our weight in newtons, because it is the force and the unit of force is newtons. So we write the weight. Weight is also a force, and we write the weight in newtons. And the mass is written in kg and not the weight. So then we also studied about the characteristics of the gravitational force, right? That it gravitational force is an action at a distance force, that is, it does not need any contact between the two bodies. There is no need of contact. Then the gravitational force between any two bodies form an action reaction pair. We have also discussed this in the Newton's third law, that what is action and what is reaction. Then gravitational force is the weakest force in the nature. This is one of the very important characteristic of the gravitational force. It is the weakest force in the nature, yet it controls many of the things happening in the nature. Gravitational force is constant as well as conservative. Then gravitational force between any two small bodies is very small. On the other hand, it is very large between the two bodies, like the sun and the earth. Like the sun binds the earth with it. In the universal law of gravitation, we saw that the gravitational force was directly proportional to the product of the masses of the two bodies and inversely proportional to the square of the distance between them. And to remove the proportionality sign, we have introduced this gravitational constant capital G, and from that we get the force of gravitation F equals to G m1 m2 upon r square, where G was our universal constant and the value of G was 6.67 into 10 to the power minus 11 Newton meter square per kg square. This is very important. Okay, then we have written that the law of gravitation is applicable to all bodies irrespective of their shape and size. Means even if you change the shape size, still the force of gravitation between the two bodies will be same, mean keeping the mass and the distance between them the same. The distance and the mass should not change. Then the importance of the universal law. We saw that what all phenomena are carried out by the effect of gravity, the force that binds us to the earth, the motion of earth around the sun, then the presence of atmosphere around the sun. These are the all points that we have discussed till now. Then we also saw the gravitation, acceleration due to gravity, that its SI unit was meters per second square. It was a vector quantity as it is acceleration. We also saw in the chapter of motion that acceleration was a vector quantity, and here this acceleration is due to the gravity and its direction is towards the center of the earth, and its magnitude is 9.8 meters per second square, and we can also approximate it to 10 meters per second square. 10 meters per second square. We can also approximate it to Then we discussed about the variation in the value of G. In the first case, we saw that if the object moves outside the Earth's surface, then in that case, the value of G was this, the new G. This new G was equals to the original value of G divided by R. R was the radius of the Earth plus H. H whole square. This was the equation which we got. It should be R square into G upon R plus H whole square. Okay, this will be the equation which we will get. And then we have the next case, that is inside the surface of the Earth. This we were discussing, which was left in the last lecture. So see, if we are on the surface of the Earth, so if this is our Earth, and we try to calculate the value of G over here on this point on the surface of the Earth on point A. So that will be given as F equals to this force of gravitation. F will be equals to capital G, the mass of the Earth, and the say mass of Earth m1 and mass of the body m2 divided by R square. Now R is the radius of the Earth. If this is the center, so this will be our radius. So but if we try to move inside the Earth surface, if we try to move inside the Earth surface, now the portion of the Earth which will make the mass of the Earth which will attract the body inside the Earth surface will be this much. This shaded portion will now be no more applicable in putting the acceleration or the force. So how do we calculate this remaining mass that is not the shaded portion? So for that we will have to calculate the mass of this Earth. So for that purpose we have the formula of volume. We have the formula for density. Density rho, it is given by mass by volume, and to get this volume, this mass, to calculate this mass, we what do? We multiply the density with the volume. Density multiplied by volume. And now how to calculate this volume? We know the density of Earth, but what about the volume? That volume we can calculate by using the formula 4 by 3 pi r cube. 4 by 3 pi r cube. This will be the formula multiplied by our density. This will be the mass of the Earth when we are on the surface of the Earth, because here R, this R is for the total radius. This R is for the total radius. So we will substitute this M1, with this new mass, and that will come out to be 4 by 3 pi r cube into rho multiplied by m2 divided by r square. Right? So now you can see that there is r square and r cube over here, and these terms will get cancelled out, and we will get the final equation as 4 by 3 pi r 4 by 3 pi r into rho into m2. This will be our original force which will be acting on the surface of the Earth. But now we are moving inside the surface of Earth with the distance of h meters. This what we have moved inside the Earth. See this that is our h meters. So now what we'll do is, now the radius of the earth will shrink, and in that case our radius r will be shifted to r minus h, because we have traveled this h distance inside the surface of the earth and the radius will now decrease. So in that case our new mass, it will be 4 by 3 by r minus h whole cube, r minus h whole cube. Now this r is shifted to this r minus h, and the formula remains the same for the sphere, r by r minus h whole cube multiplied by rho. And we know now that our formula f will now change to what? It will be 4 by 3 m1. Now m1 has changed to this, the new mass of the earth is now this 4 by 3 by r minus h, r minus h whole cube multiplied by rho multiplied by m2. M2 is the mass of the object placed on the surface of the earth. This divided by now r minus h whole square. Now because they have also traveled h distance inside the surface of the earth, so the distance between the center of the earth and the object will be now r minus h. So the final equation will be this, and you can see that there we are having r minus h whole square and there is cube. So this square and cube can be cancelled out, and we finally get that the f dash, this f dash is now equals to 4 upon 3 by r minus h into rho into m2, right? And now from this, if we divide this f with f dash, if we divide these two equations, so what do we get? F upon f dash will now be equals to 4 by 3 by r into rho into m2, and this whole divided by 4 by 3 by r minus h into rho into m2. Now you can see that we are having 4 by 3 common over here, so this will get cancelled out. Then there is this pi also, this will also get cancelled out because this is numerator and denominator are same. Now see, there is rho into m2 and here also rho into m2, so this will also get cancelled out. So finally what do we get? It's f upon f dash will be equals to r upon r minus h, and we know that the f force, that is force is equals to mass into acceleration, right? So mass into acceleration, mass is of the mass of the earth, so this mass of the earth into acceleration due to gravity, that is g, and here f dash is for the new value of g. So in that case we'll write m upon g dash, and this m will get cancelled out, and we get that g dash, our new value of g, our new value of G is equals to R upon R minus H upon R multiplied by G, right? From this, so this is the variation of the value of gravity when we move inside the surface of Earth. Okay, you can see that inside the surface of Earth, the value of G changes linearly, means here value of the exponent is 1. It changes linearly. But when it comes to the value variation in the value of G, it is changing, see, squarely, that is exponentially. So there will get a, in terms of square. So whenever we'll try to draw a graph for the change in the value of G outside the surface of Earth, we'll always get a parabola. We'll always get a parabola. But when we'll draw the value graph for the change in the value of G inside the surface of Earth, we'll always get a straight line. Okay, this is very important point. We'll get a straight line. Okay, for the case, in the case if we are plotting the graph for the change in the value of gravity inside the surface of Earth, we'll always get a straight line, and outside the surface of Earth, we'll get a parabola. Okay, because here it is changing linearly, and outside the surface of Earth, it is changing exponentially. That is in the terms of square. Okay, so there we'll get a parabola. So the next case, that is at the center of the Earth. At the center of the Earth means the distance we have traveled inside the surface of the Earth is equals to R. So in that case, our H will be equals to R. And here we have seen that the change in the value of G or G dash, see this, is equals to R minus H upon R multiplied by G. So our new value in this case, G will be equals to R minus H. So in this case, our H is equals to R. So we'll substitute this H with R divided by R into our old value of G, and this is our new value, that is G dash. So you can clearly see that R minus R will be equals to 0, and 0 multiplied by anything will be equals to 0. So this will be equals to 0. So our new value of G, inside the surface of Earth is 0. It is 0, and it is also written over here that at the center of the Earth, the value of gravitational acceleration is 0. The value of gravity acting at the center of the Earth will always be equals to 0. Okay. Then we are checking at the poles. What will happen to the value of gravity at the poles? That it is, see, Earth is flattened at poles. Earth is flattened at poles means the shape of the Earth is not perfect sphere. It is somewhat like this. A perfect sphere will be looking like this. See, and here the distance. This distance is less. This vertical distance is less than the horizontal distance. And in this case, see this over here, the vertical distance is equal to the horizontal distance, and our shape of the Earth is like this. It is flattened at the earth, means flattened at the poles, means the distance at the pole from the center is less than the distance of the equator from the center. This distance is more at the equator. Okay. So because of which, thus the radius of the earth is less at the poles than at equator. Hence the value of G is less at the equator than at poles. We have seen that the distance is inversely proportional to the force, and the force is because of the this value of G, and in that case, or the value of G at the pole will be more. Why? Because this distance is less, and as the distance decreases, our force increases, and force increases because of the increase in the value of G, that is the gravity. Okay, so the G is more at poles. G is more at poles. At poles. G is more at poles. The value of G is more at poles than at the equator. Why? Because the radius of the earth at the pole is less than the radius of the earth at the equator. Okay. Now we'll move on to our next topic, that is the mass and weight. Mass, we have seen that it is a fundamental quantity which is having its SI unit as kg, and weight was the normal force acting on the object standing on the surface of earth. So this is a comparison between the two, that is mass and weight. See, mass is the amount of matter present inside the body. It is a total amount of matter. The total amount of matter. It's how many atoms, molecules are present inside it. It is given by the mass. But weight of an object is the force with which it is attracted towards the earth. What is weight? Weight is the force and the force of attraction with which the object is attracted towards the earth. With which the object is attracted towards the earth. Then mass is a scalar quantity. We have seen that it is also a fundamental quantity, and all fundamental quantities are scalar quantities. But weight is a vector quantity. Why? Because it is a force, and force is a vector quantity. We have seen it earlier. Then mass is measured in kg, that is kilograms, but weight is measured in newtons. Why newtons? Because weight is a kind of force, and force has a unit of newton, and mass we have seen it in the fundamental quantities, that it is a measured in kilograms, but weight is measured in newtons. This is very important point. Okay, then mass always remains constant. Mass will never change until and unless you cut the object into two pieces or n number of pieces. But if you don't do that, mass will always remain the same. But weight will depend on the value of G, that is gravity, the acceleration with which it is attracted towards any object. In this case, it will be the surface of the earth, right? So if we change the value of G, like if we move above the surface of the earth or inside the surface of the earth, the weight of the object will start changing, but mass will always remain the same. Whether we move the object above the surface of the earth or inside the surface of the earth, it will always remain the same. Then mass cannot be changed. We cannot change the mass physically, means like if until and unless we don't make physical changes in it, like cutting it into pieces. But weight can be changed by changing the value of g, right? That we have discussed in the above point. Then mass of an object can never be equals to zero. If there is some object, it will at any instance will have some or the other value of mass. You can see the air, you can see any atom, even if there is a presence of single atom, it will have some or the other mass. But the weight of an object can be made zero. How? When the value of g will become equals to zero, what will happen? If the value of g is equals to zero, what will happen? The weight will also become equals to zero. The weight will also be equals to zero. And if we move at the center of the earth, I've seen that the value of g is equals to zero. So in that case, our weight will also become equals to zero. So this was the difference between the mass and weight. So we'll move on to our next topic, that is weightlessness. Okay. So what is weightlessness? The weight felt by a body near the Earth's surface is called as the actual weight. We have also seen this in the case of the lift, that what is actual weight and what is the apparent weight. Actual weight is the weight of the body near the Earth's surface. Then the deviated value of weight of an object due to variation of g is called as the apparent weight. What is apparent weight? That is the deviated value, means the changed value due to the variation of g is called as the apparent weight. Now see, in this situation of weightlessness, the effective weight of the body becomes zero, means the weight at that particular position will become equals to zero when the value of g will be equals to zero. We have already discussed in the section of mass that mass will always have some value. It will never be equals to zero of any object, but weight can be made equals to zero when the value of g is equals to zero. So in the situation of weightlessness, the effective weight of the body becomes zero. So when the weight becomes zero, the value of g over there is equals to zero, is equals to zero. So to achieve weightlessness means the condition where the weight is equals to zero. What we can do is there are these four conditions, that during a free fall under the effect of gravity, our weight will be equals to zero because there will be no normal force acting on us. Then inside a spacecraft or satellite, we have also seen many cases or the videos where the person sitting inside the satellite experience weightlessness. They are not stick to the surface of the satellite or their aircraft. So this is because their value of gravity is equals to zero, and because of which they feel weightlessness. Then at the center of the earth, we have discussed it recently that at the center of the earth, the value of g is equals to zero. So in that case, we'll experience weightlessness. Then also, when a body is lying in a freely falling lift, we have also discussed this in the section of lift, the last chapter, right? So inside a freely falling lift, also the weight of the object will be equals to zero. And see next, the weight of an object on moon. As mass and radius of the moon are less than that of the earth, the mass as well as the radius of the moon are less than that of the earth. So the force of the gravity at the moon is also less than that of the earth. We have seen that it is inversely proportional to the distance between the two objects and the product of the masses. So in this case of moon, the radius as well as mass of the moon is less. So because of which the value of the moon's gravity is g upon 6. G, what is g? G is the value of gravity on the surface of earth. Okay, so it is 1 by 6 times of the value of g on the surface of earth. So see, there is an example. If a body weighs 60 newton on surface of earth, it will be 10 newtons on the moon. Means 1 by 6 of the weight of the object on the earth. See, the weight of the object was 60 initially on the surface of earth, and now it is 1 by 6 on the surface of moon. So we'll multiply it by 1 upon 6. That answer is equals to 10. Right? So in this way, we calculate the weight of an object on the moon. Now we'll discuss about the planets and satellites. So now what are the planets and what are the satellites? See, the heavenly bodies that revolve around the sun. The heavenly bodies means the large bodies like the earth, sun, moon, planets, other planets like Venus, Jupiter, Mars. These are called as the heavenly bodies that revolve around the sun are called planets. The planets are those bodies which revolve around the sun. There are total 8 planets in the solar system, right? There are total 8 planets in the solar system. Can you name those? Name them. They are the Mercury, Venus, Earth, then Mars, Mercury, Venus, Earth, then
Pluto.
we have Mars.
Pluto.
No, Pluto is not the planet. Then we have Jupiter, Saturn, Uranus, and Venus. Jupiter, Saturn, Uranus, and Venus. And Pluto is not a planet now of the solar system. Okay. So then the heavenly bodies that revolve around the planets are called as the satellites. First, we saw that what are the planets? Planets revolve around the sun, but those heavenly bodies which revolve around the planets are called as the satellites. Then there are mainly 2 types of satellites. Those satellites are natural satellites and man-made satellites. The natural satellites are like the moon. Earth has a natural satellite, that is moon, and there are also some man-made satellites like the INSAT, and the name of the satellite, that is the Aryabhatta. It is the first satellite sent by the Earth, sent by India around the surface of the Earth. Now we'll discuss about these man-made satellites. The types of man-made satellites. There are mainly 2 types of man-made satellites. The one is the geostationary satellite and the another one is the polar satellite. The geostationary satellites are also called as the parking satellites. And see, what are the geostationary satellites? The satellites that appear to be at a fixed position be at a fixed position at a definite height to an observer on the surface of the earth. It is at a fixed position means if we look up and if we see some satellite on our head, so that will remain over there for the all time. That will be there at all times. It will not change its position until and unless it is told to change its position manually. Okay, it will remain there as itself. So because of which it is, they are also called as the parking satellites. Right? When we park our car or any vehicle, it remains over there for the time till we don't come there and move its position. So it is same for the geostationary satellites. It will remain at its fixed position over the surface of the earth until and unless we don't change its position. Okay. So such type of satellites are called as the geostationary satellite. And the height of such satellites is 36,000 kilometers from the surface of the earth. And its period of revolution is 24 hours, means it takes 24 hours to revolve around the surface of earth. See, it is given that it is 36,000 kilometers. It is not meters, it should be kilometers. And the geostationary satellites revolve around in this geostationary orbit. Okay, and to complete one revolution around the surface of earth, it takes 24 hours. And earth also takes 24 hours to rotate around itself. We have seen the difference between the revolution and the rotation in the chapter of motion, that in the circular motion and rotatory motion, right? So they are, these geostationary satellites are used to reflect TV signals and telecast TV programs from one part of the earth to other. Now, if there is some program going on in USA or say Germany or say in Britain, we are able to view these TV programs on our TV. Why? This is only because of the geostationary satellite, because they help to reflect the TV signals and telecast TV programs. Right? So this is possible because of the geostationary satellites. And these geostationary satellites are present in the geostationary orbit, and this geostationary orbit is at a distance of